I'm Erika Reinhardt. I live here in San Francisco, and I'm one of the co-founders of a nonprofit called Spark Climate Solutions.
And essentially, what is it that Spark does?
We work on accelerating progress in high-impact emerging climate fields to work towards climate restoration.
Okay. And can you just give us a rundown, your personal journey, how you ended up here?
Sure. My background is originally in engineering and within a lot of different impact-oriented projects. But as I started learning more and more about the climate crisis, it became clear that it was one of the most fundamental and challenging challenges that we faced, and was the underpinnings of so many of the other things that I personally cared about. So I decided to make a big career transition and focus solely on trying to help address climate change. I didn't decide to go back to school. I took some time off to learn a lot, both from IPCC reports and talking to many people, and then figuring out how I could apply the things that I was already good at, engineering, management, etc., and then apply that to climate sort of with my newfound climate knowledge and many, many very smart collaborators.
Yeah. And just again to expand on that slightly, did you feel that, without, I'm not trying to put words into your mouth at all, but did you feel that the way things were going, we just went up to it?
It became obvious that this needed to be an absolute all-hands-on-deck effort, and that we're not already on track, and so more effort and help was needed to get closer to that. And as I dug in more, it became also clear that there were a number of areas that were really in their very early stages and needed a lot more support in order to get to the point where they might be able to be a part of the suite of climate solutions that would be necessary to help us get to a more stable state.
Okay, great. And so leading on from that, can you just kind of define the role of Spark?
Sure. So Spark exists to help really catalyze action and build solution ecosystems around very emerging climate areas. And so we are solely focused on impact and looking at how can we better understand all of the different levers that might be necessary in order to fully address this problem, and all of the interdisciplinary pieces to get that done, and then help to support that happening in the world. And that means a lot of different things, from spinning up new projects ourselves, doing work ourselves, and also helping to fund and start other work in the ecosystem and really build sort of collaborative networks of people and organizations solving these problems together.
Can you just talk me through the recipe? I mean, a group of you were in a bar one night or a coffee shop and you thought, let's get together and start an organization. What was the process?
It was during COVID, so it was a lot of Zoom calls rather than coffee shops.
Oh, I'm sorry, can you start that again as a statement?
Spark came about really from a series of conversations between myself and my two co-founders. We were all circling around these same questions around what's missing and how do we help catalyze more action on climate. This was during COVID, and so this was all over Zoom calls and a few in-person meetings. We weren't in the same part of the country. And we started realizing that there were a few areas that repeatedly came up as ones that we thought were really high impact and high potential in their very early stages, and that we didn't see a lot of other action on yet. And so part of Spark's hypothesis that we're building out right now is that there are these models that we can add to what's already happening that can help to support more action on a number of different dimensions, in particular with a focus on helping to bring new solutions into the portfolio of things that will be available in the future.
Did you find that, I mean, there's a number of scientists even that we've interviewed, from Renault and Rob Jackson and people like that. Were all these people already connected, or was there a degree of kind of siloed research going on and you were able to kind of connect these people? Or?
In these very early fields, we see that there's small communities that are starting to form in order to start working on them, which is wonderful. But we've also found that there's a lot of missing connective tissue. And that's true within the research communities, where there are sometimes different researchers working on different portions who aren't yet collaborating together. It also is also true to different parts of the community that ought to be working on this problem but aren't yet, and so helping to pull more people in. And there's a whole nother community of folks that need to get involved here that often aren't yet educated on the details of this early research, that we can help to educate them and help them understand what role they may have to play in these as well, be that funding, policy, governance, et cetera. And so we view one part of our role as being to help build much stronger, more interconnected communities that are pulling more people into these fields and strengthening what the folks who are already in the field are able to do with additional support.
Give me a kind of a 101 lead in terms of methane itself, and then lead into what you're talking about.
Okay, great. Methane is an incredibly potent greenhouse gas that is currently causing at least 0.5 degree Celsius of global warming. It has different sources than CO2 does, and only recently is starting to get more attention on its importance. Methane comes from a wide variety of anthropogenic, human-caused sources, as well as natural sources. Human sources are different sections of agriculture, different leaks from gas and oil systems, and also different types of waste, landfills, wastewater, et cetera. We've also always had some natural emissions from things like wetlands and termites. But the overall methane emissions have dramatically increased due to human-caused activities, both human-driven sources of methane, as well as now climate changes that are accelerating some of those natural sources. Tackling methane is incredibly important in the overall picture of how we can mitigate climate change and work towards climate restoration. And the reason for that is that because it is so potent and also so short-lived, we have an opportunity by cutting methane to help to actually start bringing temperatures down, while in parallel we tackle carbon dioxide and other greenhouse gases that are more long-lived. And so within methane, it's a very broad field, and there are many different priorities. We absolutely need to be deploying all of the abatement and avoidance solutions that we have in all of the various sectors in order to start shifting the curve. Unfortunately, we don't yet have solutions for all sources. And so in parallel, we also need to be investing in research and solution development to help address the areas where we don't yet have the tools that we need. Anthropogenic methane emissions reduction is a really huge and important part of the overall methane problem and needs to be priority one. However, natural methane emissions are also increasing, and we have fewer controls over those emissions. Plan A is always to mitigate overall climate change in order to mitigate those emissions in the first place. But at this point, we need a plan B as well. And that plan B is starting to understand if there might be ways that we can help to remove that methane from the atmosphere more quickly than it naturally would break down on its own. And that's the field of atmospheric methane removal research, which is a very important research field at this stage to start understanding whether or not there are solutions available that may be able to achieve these goals and push forward their development.
On the, can I just go into the possibilities around the research of methane removal? Because my understanding is that generally that research is following the path of potentially accelerating natural methods of methane removal. Is that correct?
There's a number. The reason that methane is so short-lived in the atmosphere is that it has a number of ways that it naturally breaks down, and that happens in the air, and that also happens in soils. And so some of the techniques that are being looked at for how we might some of the techniques that we're looking at in order to how we might be able to further accelerate the removal of methane in the atmosphere is taking inspiration from those natural methods, either in the air or in soils. There are other methods also being looked at that are more engineered systems, and those have some pros and cons as well.
Okay. What would you say are some of the biggest challenges to the research that's being done at the moment?
The challenge of developing atmospheric methane removal methods is in finding methods that can address very low concentrations of methane as there are in the atmosphere, that are also highly scalable to address the massive amounts of atmospheric methane that we have, and doing so in a way that is beneficial, that is not using too much energy, doesn't cost too much, and doesn't have any other negative side effects. The reason that this can work is that methane is so potent that even at low concentrations it does have a very big impact. But because really of that low concentration, as well as some of the chemistry around methane, it is a very challenging problem. Fortunately, we have more and more brilliant scientists who are working on it, looking at a range of different methods, using different catalysts, using different biological systems, using different atmospheric chemistry in order to try to start figuring out what solutions may achieve all of these goals.
The interview I did with Renaud in France, he was talking about three main areas. One of them was the iron salt aerosols. What are your thoughts on that? How promising do you think that is?
Iron salt aerosols are one method that is currently under research to determine whether it might be a potential atmospheric methane removal solution. Iron salt aerosols are something that engages with atmospheric chemistry. It's something that happens in the air. And so right now, this really is at a stage of very early scientific inquiry, starting to understand how does this chemistry work? What are the side effects? How might we globally model what this would do? Our goal as a research community is to get to a point where we, for iron salt aerosols and other methods, can understand how safe, how, at what cost, at what, sorry, let me start that sentence again, because that was not a proper sentence. The research goals for iron salt aerosols, as well as other methods, are to get to the point where we understand what options may be on the table, and that to answer that, we need to answer questions around scalability, cost, how these things might be deployed, what other side effects they may or may not have. Iron salt aerosols, it's in very early stages of research, and so these are all things that we're starting to have scientists study with computational models and lab experiments in order to really understand the very basic chemistry of what's going on.
Is your instinct that this is a promising avenue?
Iron salt aerosols are a method that potentially hold a lot of possibility as a highly scalable solution. However, there's a lot of questions to still answer before we know that for sure. Things like, what's the efficiency of this process? What are other side effects? Where might this be deployed? How would it safely be done? And so these are all questions that we need to answer for this solution, as well as any other solution that's evaluated, to really understand what its potential is and whether it has a place in our overall suite of solutions. There are multiple different avenues that are currently being researched for the methane removal potential. Some of these include things like looking at soil bacteria that currently are removing methane from the atmosphere and how that might be able to evolve. People are also looking at different types of catalyst systems. Those are something called thermocatalysts that use warm catalysts, the thermo part, in order to make these reactions go faster, and photocatalysts that use energy from the sun or from other light sources in order to power these reactions. There are currently multiple different types of solutions that are being studied for their methane removal potential. Some of these are biological, looking at how soil bacteria already today naturally consume methane, and whether there's more that we can do with soils in order to help address atmospheric methane. There are also a number of methods that use different types of catalysts. Some of these use heat, and some of these use light as input power sources to help to make these reactions go faster.
Great, okay, let's speed. So yeah, just a general overview of where we're at.
Where we're at right now in the methane removal field is that this is really early research. It's incredibly important because we may need this category of solutions to help address, in particular, natural systems emitting more methane as the climate warms from things that we're already doing today. But we don't know yet what these solutions may be on the table or not. And so it's really important that we don't rely on these solutions yet coming, and that we make very clear and that we act in such a way that, let me do it again. Methane removal is a very early and also very important research field. We don't yet know what the different solutions here may be, and active research is going into that. The reason it's so important is that we need this category of solutions to exist, if we can find safe ones, in order to help address increasing natural emissions of methane that we don't have other ways of mitigating today. However, we don't yet know which solutions will be on the table and whether any will be. And so it's also incredibly important that we be mitigating all methane emissions that we possibly can and reserving whatever capacity we may have here in the future for emissions that we couldn't have cut, in particular natural emissions. And so one of the really important things as we think about any new emerging climate field, including methane removal, is that this is always about adding to our portfolio of solutions available. We always need to be deploying all of the mitigations that we have available to us while investing in hopefully having even more tools down the road as we may need them. A few really important things to understand about where we are with methane removal today. First is that this is still a research field, and we can't depend on the availability of future solutions here. Second is that this will always be a tool that needs to be used in complement with other existing tools. We need to be addressing carbon dioxide, certainly, and within methane, we also need to be cutting all possible methane emissions that we can today and investing in research for other direct methane abatement opportunities, while we also understand what we might do with that remainder, primarily from natural systems, which could be methane removal. So this really is, like so many other areas of climate, a yes and solution. There's no one solution here that's going to solve everything, and this is all about adding new tools to our toolbox so that we can have a more robust climate response and mitigate the many different flavors of risk that we unfortunately face today.
That works. That's great.